In this little video, we're just going to go through electron configuration, and we're going to just put a little bit of an AS spin on it. So let's have a think first of all of a calcium atom. Now, calcium atom, you may remember, is the largest atom that we actually go up to in terms of electron configuration at GCSE. So calcium has 20 protons and 20 electrons. So if we put those electrons in, we know that there are 2 in the first shell, followed by 8. Then another 8, and finally we get 2 in the fourth shell, and that's where we stop. After calcium we go into the transition metals. So why do we stop at calcium? What is so special about calcium, and what's going to go wrong if we head into the transition metals? Well, let's have a look at those electrons for calcium. If we can think of those electrons as being in energy levels. So the lowest energy level, that first shell, is we call n equals 1. The second shell, n equals 2, and so on. And as the shells get higher in a numerical value, they also get higher in energy. So we call n the principal quantum number, which before we've always used to call it the shell number. However, the reason why we stop at calcium is because we haven't actually told you the truth. The third shell can actually hold 18 electrons, and the fourth shell can hold 32 electrons. So where on earth are all those electrons going? Well, what we do is we separate those shells into subshells, and this is given another quantum number. It is called the angular momentum quantum number, and is given a letter. It can be either an S subshell, a P subshell, a D, or an F subshell. So there are 4 different types of subshell that make up our shells. Our first shell is made up of just one subshell, and that's the S subshell. An S subshell can only hold 2 electrons. What does an S subshell look like? Well, it's not particularly exciting. It's how you imagine the shells to be. It is just a sphere around the nucleus. When we go into our second shell, it's also going to be made up of a S subshell, as is the third and the fourth. So every shell has to have an S subshell. And you can see how we denote those, that we have 1 S, the 1 is for shell number 1, and S is for subshell, up to 4S. 4S is my fourth shell, and the S is a subshell. And as I said, each of those can hold 2 electrons. So the next one is a P subshell. A P subshell can hold 6 electrons and has a slightly different shape. It is called a dumbbell shape, and it's a bit like if you take an S orbital and you squashed it in the middle around the nucleus. So it's got 2 lobes either side of the nucleus, and we've shown it there along the 3-dimensional axes. So when we put our 6 electrons for the P subshell with our 2 electrons from the S subshell in the second shell, you'll be able to see that we've actually got our 8 electrons. So our second shell is made up of a S and a P subshell. So the next one we need to look at is going to be our D subshell. Now our D subshell can hold a maximum of 10 electrons. This is one example of what a D subshell would look like. Very strange. But as we said, we can have a total of 10 electrons in our D subshell. And so if we pop those in, you can see that our n equals 3, which has 18 electrons, can be made up of a D, an S, and a P. So just before we move on, let's have a quick look at the 4F subshell. So this is a representation of what it may look like. This is 4F, and as I say, it will have 14 electrons, and that gives us our 32. So we now have our principal quantum number, which is our shell number, and our angular momentum quantum number, which refers to as our subshell. So we're going to break this down a little bit further into smaller units called orbitals. Now an orbital is a region of space that can hold a maximum of 2 electrons. So each of these subshells is divided now into orbitals. So let's have a look at what they look like. So here we go. Here are our S orbitals, first of all, and we would just say that they're going to be slightly bigger spheres. let's have a look at our p now. So we're going to have 3 p orbitals, and all the time they're labeled px, py, and pz. So px has lobes along the x-axis, pz along the z-axis, and y along the y-axis. So it may take a little bit of imagination to picture those in 3D, but you can hopefully see how they differ from each other. And if you're asked to draw one of these in the exam, you do need to be able to draw the right one. Just remember, if they ask you for the pz, you put the lobes along the z-axis. And the 3p and the 4p look exactly the same, just slightly larger. These different orbitals are given the quantum number labeled ml, and that's called the magnetic moment quantum number. So we now have our 3 quantum numbers. We have n, l, and ml. But for to describe an electron's position, we need actually 4 quantum numbers, and that's because no 2 electrons can have the same set of quantum numbers. And at the moment, if we had 2 electrons in a 1s orbital, they would. So what we do is we have the 4th one, which is called electron spin. An electron spin is either plus a half or minus a half, and we denote those by arrows, half-headed arrows. The plus a half is going up and minus a half is going down. And when we start filling these orbitals, we must always put 1 electron up and 1 electron pointing down. Now I'm sure you've all noticed there's something slightly odd going on here as well. If you look at the 4th shell, and particularly focus on the 4s and the 3d subshells, you'll notice the 4s is actually lower in energy than the 3d. And so when we actually start putting electrons in, it's actually the 4s that fills up first before the 3d. And if we now look at calcium, we start putting our electrons in. We've got a total of 20 electrons to put in, and we start from the lowest energy orbitals. And if we put our electrons in, you can see our final electrons going to the 4s before we start going into the 3d, which is why we stop at calcium at GCSE. And how are we going to write the electronic configuration of calcium? At GCSE, we said it was 2882. So we can actually be a little bit more specific, and we would say it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We generally don't break it down into orbitals. We just say we put all the 3p orbitals together to say we've got 6 electrons in total in our p subshell.